take a look at random variables in this particular video. So a random variable is a variable whose value is based on some kind of random event. Right? We're coming out of this unit on probability. We're going to talk about probability a little bit more, but this is another way to kind of start to use probability and build off of it. So there's two types of variables out there. As a reminder, you got discrete, where we can list all of the outcomes. There's a finite number, so like flipping a coin and get 2 heads, 3 heads, 4 heads, making a free throw in basketball. Right? We can't hit 2.5 free throws. We can't hit 6.8 free throws. It's 1, 2, 3, 4. It's countable. It's discrete versus the other one that we've talked about before, which is continuous, which we can take on a value, an infinite number of values within some given interval. So heights, right? You can be 6'1", 6'2". You could be 6'1 and a half. You could be 6'1 and a quarter, so on and so forth. Arrival times, you could get somewhere at 3 o'clock, 3:01, 3:02. You could break it down to the second. And really, anytime you have a normally distributed uh, variable or any kind of normal distribution, typically that's going to be some kind of continuous outcome. What we're interested in is discrete random variables, countable. So let's say we have this grade distribution. So students in this intro stat class had the grade distribution is 21% had A's, 43% B's, 30% had C's, 5% D's, and 1% of the students were failing. So first thing you want to do as you start to set up these random variables is you want to define a variable. So we'll call X the grade of a randomly selected student, and we'll just put it on a 4-point scale since we're kind of familiar with that. So the values that X can take on, you can see right there, would be 4, 3, 2, 1, and 0. So there's your A, B, C, D, and F when you're looking at those. And then what we do with our probability distribution is we go ahead and drop our probabilities into that particular chart. And from there, now all of a sudden we could use a distribution, right? We could say, what's the probability a student receives an F? Well, we just look right here in this last piece of the chart right there, and that'd be, 0.01. Well, it slid off of it a little bit, but as a probability statement, probability that X equals 0, right, that X takes on that value of 0, which we've assigned to be an F, is 0.01. What's the probability they receive an F or a D? Well, we already know how to deal with ORs. So it'd be probability that X is 0 or X equals 1. And so you just add 0.01 plus 0.05. And then how about probability of student receiving a grade higher than a C? And the thing to point out here is you could write that as probability X is greater than 2, right, above a C. Another way you could write that out, greater than or equal to 3. And there's actually a few other ways that you could write out these probability statements, like you see right here. Trying to get that to slide underneath a 3. There's a few different ways of writing it. You can kind of disregard, but all trying to say the same thing. So let's say that we're going to flip a coin, and we'll make Y the number of heads after tossing a coin 4 times. So let's come over here. So we'll define Y, number of heads in 4 throws, or in 4 tosses. So first off, one of the things to consider as we're making this probability distribution, let's think about what are the values that Y could take on. So how many heads could we get in 4 tosses? Well, there's a possibility we could get 0 heads. We could get 1, we could get 2, we get 3, or we could get 4 heads, right? And then within those, they're not all as equally likely, right? We start thinking about this. 0 heads, well, that'd be tails, 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 tails. But to get 1 head, right, all of a sudden, well, you could get heads first and then all tails. You could get tails, then 1 heads, then tails and tails. You could get 2 tails, your heads, and then a tails. Or you could get 3 tails in a row and then heads, right? So it's a little bit more likely you get 1 heads, right? There's 4 options than 0. So these are things to consider as we start to build our probability distribution. So here's Y, and these are the values Y can take on. And underneath Y, in the second row of that column, what we're going to do is come up with the probabilities of these things. So right off the bat, we'll start with 0 heads. So we just said this was tails, 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 tails. So the probability of getting tails and tails and tails and tails, well, that's 0.5 times 0.5 times 0.5 times 0.5. Should be 0.5 to the 4th. And 0.5 to the fourth. You could write that as 1 over 16 if you'd like. We'll go ahead and do it as a decimal kind of here in a second to make a little bit more sense as we go. Probably the next easiest one to calculate would be 4 heads. Well, that's just heads, 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 which would be, again, 0.5 to the fourth, which is 0.0625. Well, we just saw this. There's 4 scenarios, right, up here that I just wrote down for 1 heads. Each one of those scenarios, if you think about it, that's 0.5, that's 0.5, that's 0.5, and that's 0.5. Well, this would again be 0.0625. However, there are 4 of those, right? That's 0.0625. This is 0.0625. This is 0.0625. So if this right here is going to actually be, you know, we end up with 4 of these 0.5 to the fourths, which should put us at right at 0.25. Same idea if you think about this for just a moment. 3 heads would essentially be the exact same thing as 1 head, except you're switching the T's and the H's around. So really we have 4 scenarios again, right? Tails, heads, 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 tails, heads, heads. But again, each scenario is a 0.5. And so again, 0.25. And then there are actually 6 combinations of 2 heads and 2 tails. Or another way to think about it, this probability should sum to 1. And so since we have 4 out of the 5 already filled in, we could just go ahead and subtract from 1. And that would leave us with 0.375. So the probability that we toss, you know, we could now use our table. Let's say a question asks us, what's the probability of at least 2 heads? Well, we look very closely. At least 2, we could rewrite that probability that x is greater than or equal to 2. And then it's just a matter of we would go to our table. At least 2 would be the sum of those 3 boxes together. So you could do the 0.75, or 375, excuse me, plus 0.25 plus 0.0625. And that would be 0.68. Oh, excuse me, let me clean that up a little bit. That'd be 0.6875. So the probability we throw at least 2 heads in 4 tosses, 0.6875, right? So we'll look at another situation. Sorry, I'll flip through this. We just did all that on that chart. So suppose that we have these monkey shaving kits, and people can either buy an electric monkey shaving kit or a gas model for shaving their monkeys, because even monkeys need a good shave every once in a while. So according to Consumer Reports, because there's a lot of research done on this, 40% of customers will select electric model, 60% choose a gas model. So we're going to go ahead and find the probability at least 2 out of 4 customers will choose the electric model. So we'll go back to our blank screen here, and we'll get things going here. So we're looking for the probability at least 2 out of 4 choose electric. All right, so that basically gets us going in the direction of what our random variable needs to be. So x is going to be number of customers out of 4, that's important, that select electric. So if we look back very quickly at our example, the probability that we select an electric is 40%, so that's important. So the probability of electric is 40%, which means the probability that they select a gas model is 0.6. And think about this for a minute. What are the values that x could take on? So how many customers out of 4? Well, 0 could pick it. 1 could, 2, 3, or 4. Not all of those, just like you think about back with the coins, they're not as equally as likely. You're probably more likely to get 1 or 2 customers that select, if we're randomly picking, than we would to get all gas or all electric. But we still have to consider it because we're randomly selecting these folks. So go ahead and set up our probability distribution. So x can take on the values 0, 1, 2, 3, or 4. And now it's just a matter of kind of thinking through what do those scenarios look like to fill in the actual probabilities. Keeping in mind too, these should sum to 1. That's still one of our probability rules. So let's start thinking through this. So it's if 0 people pick electric, that would mean that we get 4 gas customers. So gas, 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 which would be 0.6 to the 4th. So this first number, 0.1296. The next easiest one to go get, I still think, is the other side of the chart. Well, what's the probability we get 4 people that prefer electrics? Well, there's only one way to get electric, 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 which would be 0.4 times 0.4 times 0.4, which is 0.0256. So more people prefer gas, as you can see right there. So it'd be there's a higher chance we get 4 gas customers, about a 13% chance, versus about a 2.5% chance that we get all electric. And you can kind of see that because gas was more popular for monkey shaving, which probably most of us already knew. Now kind of start filling in the rest of the chart. So let's think about one electric customer. So maybe we get electric, gas, gas, gas. It could be gas, electric, and then customers 3 and 4 would be gas. Or maybe customer 1 and 2 prefer gas, 3 electric, 4 gas, and then on down. So there are 4 ways to get one customer. This is a little bit different than we saw with our coin flipping because it's no longer a 50-50 shot. In fact, we have a 0.6 chance of getting a gas and a 0.4 of getting electric, but in each one of these scenarios there are 3 G's. So what we'll do is we'll take that 0.6, we'll raise it to the third, we'll multiply times 0.4, and then there are 4 of those scenarios. So in total there are 0.3456. I think the next easiest place to go fill in will be 3 electrics. So again, you could do electric, 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 gas, so on and so forth. And just like with 1 back here, there are going to be 4 combinations. But this time, we have 3 people that would choose electric and 1 person that choose gas. And we're multiplying by 4 right there again because we're considering there's 4 different ways to put these, to put the 3.4s and the 1.6 together. And so that puts us at 0.1536. And again, my suggestion to you, there are actually 6 combinations for 2 E's and 2 G's, or probably the quicker way, again, these should sum to 1. So what we can do with that is add up what's there, subtract from 1, and that should leave us with 0.3456. Now that we got our table done, which is the tricky part, go up and answer the question. What's the probability at least 2 out of 4 choose electric? So what's the probability that x is greater than or equal to 2? All right. And so look carefully in the chart. That would be the 0.3456 plus 0.1536 plus 0.0256. And that would be, 0.5248. So there's about a 52% chance that at least 2 out of 4 customers would prefer, or I could say this, at least 2 out of 4 randomly selected customers would prefer the gas or electric model monkey shaving kit.